So in the previous slide, we talked about the PCA and the LDA, and these are the most popular linear dimensionality reduction algorithms for supervised learning case and unsupervised learning case. Okay, so now I want to talk about something else. So before talking about some other kind of algorithms, I want to talk about the cocktail party problem or blind source separation. For example, in the cocktail party, there are a lot of people talking at the same time, but when you talk to your partner, then you can understand what he says, right? Because we can focus on him, or we can separate his voice from other background noise or other people's speech signals. So technically, source separation and the target source extraction, these are kind of two different kind of tasks, but basically we use the same kind of algorithm, similar algorithms and the similar principles and the theories. Okay, so in this slide, I want to just talk about the source separation, okay? As I said, it's not easy to understand what one person is saying in noisy social settings, but we can do that, okay, because we can pay attention to a particular stimulus, okay, and then we can filter out the others. And we need to separate independent signal from mixed signals. So this is what we do in a cocktail party, okay. So this is a source separation problem, but as I said, it's similar to target source extractions, okay. So we can formulate the problem in this simple kind of framework. First, we have a lot of sources. In a cocktail party, we have many speakers, and also we can have some other kind of noises, musics, and some other noises. And we mix this signal. So we have microphones. And in this equation, we assume that we have 4 microphones, which means we have 4 mixed signals, assuming that we have 4 independent sources. So this is the simplest formulation for source separation, okay. Sometimes we have a smaller number of microphones than the sources. Sometimes we have more microphones than the sources. It depends on the situation, but this is the simplest one. Okay, so now we have observations, and from these observations, we have to estimate the sources, okay. So we assume that this X is A times S, and S is the sources. And this is the simplest one because this one is a linear instantaneous mixture. So S is mixed with this simple linear transformation. And then the mixing is also straightforward and simple because A is a linear, then the Y is W times X. And if it's the best, and if it is an ideal case, then W should be A inverse. Then Y is A inverse, X is S. We can estimate S with Y. Okay, and then ICA is one of the most popular source separation algorithms. Okay, so it is a statistical method to decompose given multiple data into a linear sum of statistically independent components. This is important, statistical independent components. So in PCA, we actually maximize the variance in the projected space. So this is the direction because in the projected space, this one can preserve the most of the variance. But in ICA, we are not interested in just the variance. We are interested in a statistical independent component. Okay, if we assume that the distribution is a Gaussian, then as long as we make an uncorrelated covariance matrix, then it is independent. But in ICA, we assume that the sources are not from the Gaussian distribution. Sources are non-Gaussian. Gaussian distribution is all about the noise, and it's not that interesting signal. So our interesting signals, source signals, are supposed to be non-Gaussian. Okay, so uncorrelatedness is not enough, and maximizing the variance is not enough. So we have to think about the higher statistics to make independent components. So for example, given 2D vectors x1 and x2, then the x1 and x2, these are the observations, and we believe that x1, x2 are generated from this mixture equation. Okay, and in this a1 and a2, these are basis vectors, and in the PCA, eigenvectors are basis vectors, but in the ICA, these are not eigenvectors. And S1 and S2, they are the basis coefficients. Okay, and the constraint is that S1 and S2, they are statistically independent. And in PCA, S1 and S2 are supposed to be uncorrelated, not independent. So if we assume that the sources are Gaussian, then the uncorrelatedness is enough. Okay, so now let's talk about some equations for ICA. So with the linear transformations, mixing is AS, as I said, and demixing is YI is WI transpose X, or simply Y is W transpose X. It depends on the slides. Sometimes we use Y is WX, sometimes Y is W transpose X, depending on the slide. So be careful with these notations. In this slide, it is W transpose. Okay, and then the likelihood of X is like this. So when we have a transformation like this, okay, and then assuming that W is A inverse, okay, then the X is W inverse S. Okay, so when we have a linear transformation, then this matrix, the determinant of this matrix is the volume change. So we have to reflect that with this determinant here. Okay, and then we assume that the sources are independent. So instead of P of S, we have a product of P of Si. Now, when we have n observations of X, then we assume that all these samples are independent. Okay, so we have a product here, and we have a P of X, and P of X is here. So we have a product and the P of X with a product, another product from here. Okay, and then if we apply the log, then this is log likelihood, and then finally we take a negative log likelihood or NLA because we want to minimize this objective function. So we have NLA. So this is our objective function, okay, and the W is our parameter, okay, and then the YTI has a parameter too. So we have to minimize this objective function with respect to W. But there is one problem. We don't know what Pi of Y is. So we assume that the source signals are interesting, which means source signals are non-Gaussian, but we don't know exactly what kind of distribution it is. It could be Laplacian. Then okay, so if it is a Laplacian distribution, then what is the parameters? So we don't have any information about these source signals. Before talking about the distribution of the sources, I want to just summarize this objective and gradient and Hessian because we need this information to train the ICA with the parameter W. So as I said, objective function is negative likelihood, which means if we minimize this one, then we maximize the likelihood. Or if you want, you can actually maximize non-Gaussianity directly. The kurtosis is a statistics to measure how non-Gaussian the distribution is. So we can actually use kurtosis to maximize the non-Gaussianity, and then that could be our objective. Or we can minimize mutual information. So when we have a Y1 and Y2, and the mutual information between these two estimated sources are supposed to be minimized, then these two are independent. That's the same as this likelihood. So anyway, if we use non-Gaussian kurtosis to measure the non-Gaussianity, then objective function is slightly different. Other than that, pretty much as long as you use the probability, then that is quite similar to this objective function. And as I said in the previous slide, we don't have any information about the P of y except that the P of y is interesting, which means it's non-Gaussian. So we don't have anything about this one, but still we can just put some kind of function notation here. Still, we don't have any information about the psi. Okay, if we know this psi, then we can take a gradient and we can take a Hessian. So depending on your kind of algorithm, we can use gradient information or Hessian information at the same time. Okay, so now let's talk about the distribution of the source signals. And as I said, these are unknown, but we can have some approximation here. So the only information that we have about the distribution is that these are non-Gaussian. Okay, so if you look at this figure, this curve is Gaussian distribution, and the blue one is the super Gaussian, and the red one is the sub-Gaussian. So either way it would be fine. Okay, so as long as it's non-Gaussian, it's interesting signal. So it could be a source. Okay, so there are two different directions. Okay, let me give you some kind of motivation about this approach. So when we talk about the direction to the city hall in a strange city, then if we have a perfect kind of information about the map, then you can say, okay, take a left and go straight 20 meters and take a right or something. So you can provide perfect, exact information about the direction. But when you don't have that kind of information, you can just say, okay, this direction, like 2 hour or 10 hour. Okay, so you can actually show the direction. Roughly, the city hall is around here. And then it's possible to find the city hall following that direction. Okay. So roughly speaking, figuratively, we can use that kind of things here. So instead of using the exact solution, we can have an approximation. Okay. So when we use a objective function and we need a gradient, and then when we take a gradient, a derivative, then this is what we need about the source distribution. And when we assume that the signals are super Gaussian, then instead of having the exact distribution and exact derivative of the exact distribution, we can just have this one. Roughly, if the source is super Gaussian, then the derivative is similar to negative hyperbolic tangent. Okay, so as long as we have right a similar direction, that's okay. So this is how we can train the ICA. So if the PI is sub-Gaussian, then we can assume that this derivative is minus y to the power of 3. Okay, then here's a question. So how do we know whether it is a super Gaussian or sub Gaussian? We don't know. So most of the time we just assume that, okay, so the sources are super Gaussian. Okay, your speech signals are super Gaussian, and some musics are super Gaussian. So many signals are many times super Gaussian. So you can try the super Gaussian. If it doesn't work, then you can assume that it could be a sub Gaussian. But anyway, usually we use this one. And there are some kind of papers to have flexible functions. So gradually it can just change between these two. Okay, there is a paper about that. But anyway, so let's not go further than this. Okay, so let's assume that we know roughly the signals are super Gaussian, then we can use this one. Otherwise, we can use this one. And then we can take a derivative and we can train. And if we use this one, then we can reconstruct this objective function. Then the objective function is something like this. Or if we assume this one, then objective function is something like this. Okay, now the next algorithm is non-negative matrix factorization. This was proposed in 1999. The NMF was a sensational algorithm because back then NMF was not proposed for source separation. It was not proposed for some other kind of specific task, but NMF was proposed to represent the data. Okay, and then when we represent the data in the different space, then we assume that everything should be positive. It cannot have negative values. Only with this constraint, then they propose the new algorithm. And derivation is not as simple, but when we decompose x with w times h, then we put this non-negativity constraint, then we have quite interesting representation here. And this one is basis vectors, and this one is coefficient. It's kind of same, right? So PCA is something like the x is wh, and w is eigenvectors, and this h is the coefficients. In ICA, w is independent basis vectors, and we have the coefficient. And in NMF, we have a basis and the coefficient. Basically, it's the same kind of equation, but they have different kind of objective function, different constraint. So if you look at this figure, okay, so when we have an image, then to represent this image with PCA, we have to use a lot of basis vectors. So these are basis vectors, actually eigenfaces, and these are the coefficients. So we, when we generate this image, then we have to have a weighted sum of all these basis vectors with a lot of coefficients. Okay, but when we represent this original image, then we can have sparse representations of NMF basis vectors. So when we look at these NMF basis vectors, these are kind of sparse and localized because we don't have subtraction in this equation. In PCA, we have negative values. We can have negative values in the basis vectors. We can have negative coefficients. Okay, so we can have subtraction here. But in NMF, we don't have any subtraction. Once you add this basis vector with some kind of numbers like 0.3, then we cannot eliminate that component from the image, whole image. So all the basis vectors should be sparse. Okay, so they are not overlapping with each other. So basically in NMF, all the basis vectors are sparse and the coefficients are sparse, so it is kind of sparse coding. And the PCA, the first eigenvector has the most information about the data, right? And the second is the second most information, and then etc. So we have to use all the basis vectors in PCA. So that's the difference between the NMF and PCA. We will talk about that later, the compact coding and the sparse coding. Okay, so as I said, all basis vectors in NMF have localized features. Okay, so both the basis and encodings are sparse, as you can see here. And the variability of X is generated by combining these different parts. Okay, this one is just the general statement. Okay, so PCA on ICA, so all the variability of X can be generated by these different parts. But in NMF, these basis vectors are like Lego blocks without the subtraction. Or if you want, you can say these basis vectors are oil painting. So in oil painting, we don't have erasure. So once you add some color, then the color stays there, right? Once you add, then you cannot delete that part. And the basis vectors define a convex cone. So when we have the data samples like this, then these are the basis vectors, and these basis vectors make this cone here. So these basis vectors are responsible for all the data samples within these cones. So we don't have to worry about all the other part. So the basis vectors can focus on the real data set. In the PCA, okay, so when we have two basis vectors, then all the space. So these two basis vectors, eigenvectors, can span the whole 2D space. But in NMF, okay, so once we have two vectors, we just span these cones, not the other part. Okay, now let's talk about NMF update rules. So first, we have to think about the objective function. So this is our objective function, but there is a constraint. Okay, W and H, they should be non-negative. Okay, so Euclidean distance is fine. We can minimize this reconstruction. Or if X can be represented as a distribution. Distribution is nothing but, two constraints. So X is positive and the sum, let's say Xij, J is 1. Then this is distribution. So if X is distribution, then we can use K divergence. Okay, then the K divergence is a little more complicated, so we can use this Euclidean distance to derive all the equations here. But if you want, you can try this one too. Okay, so for the Euclidean distance, we can take a derivative of this objective function with respect to W and the H. So we have two gradient information. So we can update this with the gradient descent. That's update rules for W, and also we can have H minus eta. Okay, this one. Okay, but there's a problem with these update rules, because what if this one is too large? Okay, then the W minus something could be negative. Okay, so in NMF, everything should be positive. Okay, but in the update rule, there is a possibility to have a negative values after this update, so that's not the right kind of direction. So we have to make sure that after this update, W should be positive, and after this, H should be positive. So if we take the learning rate really carefully, and we have element-wise learning rate, so this is our choice. Then, okay, so this is element-wise multiplication, so we can cancel this one, and we have W, then we can cancel. So finally, we have this update rule. And in this update rule, if you look at this one, then we don't have subtraction, we don't have addition, nothing, we have just multiplication. Okay, so before this update, W was positive, X was positive, H was positive, everything was positive, and we just multiply. Updated W will be positive for sure, and the H will be positive for sure. Okay, let's focus on this equation a little bit more. So if you look at this one, W, and W has a different kind of ratio. So we multiply different numbers to this W. And in this equation, X is projective to H and WH is projective to H. Okay, again, the equation is something like this. And then we check the ratio. And then if this one is larger than this one in the H space, then we increase this one. So this one is larger than 1. It could be 1 point something or 2 point something. Then we increase that element. So depending on this ratio, then we actually control this W. Okay, so we just compare X and WH from the perspective of H, and then we update W, and we do the same thing with the H here. Okay, so in NMF, as I said, everything should be positive. So when X has some negative values, then we cannot apply this NMF. Okay, so when the X is an image, okay, we can apply NMF, because in an image, all the pixels are positive, right? So usually we have intensity for the pixel from 0 to 255, or if we normalize, it's between 0 and 1. Okay, so image is positive, so we can apply NMF. And when we have a sound signal, then we can apply spectrogram, and then it's positive. Then we can apply NMF. But when we have a negative values in the data set, then we cannot apply the NMF. We have to do something to make it positive, and then we can apply NMF. Okay, so while we are talking about these representations, so I think I need to summarize the different kind of strategies here. Okay, so when we talk about the representation, we can think of local representation and discrete representation. Okay, and the support vector machines or some KNN or puzzle windows, they are based on the local representation, and all the artificial neural networks, including the ICA, NMF, PCA, these are based on the distributed representation. And the distributed representation is helpful for generalization, and it's more powerful. Okay, so let me give you some example, analogical kind of example here. Okay, so when we have a lot of samples, so let's say it's a fruit. So we have a lot of different types of fruit, apple and the orange and the mango and the melon or something. Okay, when we have a completely new fruit, I never seen this fruit. Okay, then if you try to describe this fruit based on some of these fruits, like, okay, this one is similar to apple, okay, and a little bit similar to this another fruit too. So that is a local representation. You just explain this sample based on the other sample, the sum of training samples. So think about this SVM or the KNN. Okay, if you know what I mean by this SVM, okay, so in SVM, we need a support vector. So when we have a new sample, so we actually check the kernel between the sample and the new sample, and then we find the best samples, the best training samples to find the support vectors. Or think about the KNN. So we have a lot of samples. To explain some a new sample, we check the neighbors, and then based on the neighbors, we actually classify this sample. So in the local representations, we actually check the samples locally, and then we represent that new sample based on the other samples. But in the distributed representation, we don't use the samples. We don't have to memorize all the samples. Okay, so when we have a training samples, then from training samples, we extract some factors. So based on these samples, we can say, okay, some color is important factor, and the weight is important, and the size and the shape. So we can extract a lot of features. And then when we have a new sample, even though this sample is completely different from any of these fruits, but still we can describe this sample. Okay, this one has blue color, and the weight is light, and the size is small, and the shape is sphere. Okay, so we can describe any fruit based on these features. So think about this one. When we have a completely new, completely weird, strange fruit, then the local representation has some problem to describe this one, because this one is completely different from these ones. But when we have a distributed representation, we can describe this new sample based on these features. Because even though this one is completely different, but still it has some color information and weight information and size and shape and blah blah. So we can describe this one. So these ones are the features, kind of. Okay, so now we have a distributed representation. Okay, then even in the distributed representation, we can categorize representation into compact coding and the sparse coding, or compact representation or sparse representation. So basically, compact coding can be explained with PCA, and the sparse coding can be explained with the NMF. Okay, so in the compact coding, we actually find the small lower dimensions. Okay, so now we have a compact representation. In this example, only 4 dimensions is enough to represent the data set. But in the sparse coding, we don't have a compact. Sometimes we have a bigger model, but we use a few kind of neurons or nodes. Okay, so model is much bigger or similar or bigger than this one, but still we have well represented vector here. What is the sparseness, by the way? First, there is equal response probability over the cells in our brain, and low response probability for input. So for a given input, just a few neurons are activated. Okay, but depending on the inputs, all the neurons have some kind of responsibility. Okay, so they can get activated, but not that frequently. So just a few neurons, nodes are activated, but they have equal kind of chance. Okay, and then in the mammalian visual system, there is a sparse distributed representation. Okay, and then what is the benefit of this sparseness? So with the sparseness constraint, then we can have a bigger model. So bigger model can be trained. So look at this one. In the PCA, the model is simpler and smaller, and the sparse coding, the model could be larger. Okay, which means we can model a more complex transforms. Okay, so in this case, everything should be represented based on this one. Okay, but in this case, we have a lot of different vectors, basis vectors, and then we can select some of them. Okay, so it is more kind of flexible and computationally more powerful. Okay, now to sum up this chapter, so I want to compare this clustering and the dimension first. Okay, and then I want to compare PCA and ICA and NMF. Okay, so in the clustering, we use the latent variable to assign the samples to clusters. Okay, so in k-means, this latent variable is just one hot. But in the GMM, this latent variable can be a flexible distribution. Okay, but in dimension reduction, the latent variable is not about assignment. The latent variable is about the low-dimensional basis vectors and eigenvectors and the independent vectors and sparse vectors. Okay. In the clustering, we have clusters, but there is a code book or average, and all the samples can be represented by these averages. So, for example, this example can be represented by this one, but there is kind of variability. This is kind of noise, so we can ignore this one if we represented this one with this one. Okay, so which means in the generative perspective, this sample is generated from this one. So this one has some kind of noisy variation to generate this one. Okay. And in the dimension reductions, we have a low dimensional space, and from low dimensional space, we have high dimensional space. Okay, from this low dimensional space, this is in the PCA, this is eigenvectors, E1 and E2, and we have coefficients here. And then from this one, we generate high dimension space. So basically, in the generative perspective, we use this latent variable to generate the samples. Okay. When we compress the data, when we encode the data, then we just use a cluster index for a sample, or we can use coefficient of the basis spanning the lower dimensional space. Okay. And then, as I said, noise corresponds to the variation within the cluster. Okay, so these variation will be ignored if we just use the cluster index. And in the dimension reduction, variation ignored in the projection will be considered as noise. Okay, that's the comparison between the clustering and dimension reduction. And when we compare PCA, ICA, NMF, and we're interested in the variance or non-Gaussianity or non-negativity. Okay. And then the solution is in the PCA, eigen decomposition of covariance matrix, and ICA maximum likelihood, assuming independent sources. NMF, we use reconstruction error or K divergence with a non-negative constraint. And the basis vectors are uncorrelated and independent and non-overlapping. And the coding is compact and the sparse, and ICA is somehow between this compact and sparse. Roughly speaking, it is kind of sparse coding, but when we compare ICA and NMF is sparser than the ICA, so I don't know how to categorize this one, so it's just empty now. Okay, here's one more thing. ICA is about the eigendecomposition of covariance matrix. Okay, so we have a closed form solution, but with ICA we don't have closed form solution, but PCA solution is kind of part of this ICA solution. So when we apply the ICA, we apply PCA first, and then we apply the ICA. So with PCA, we can make an uncorrelated result. Okay, so to make an independent, at least it should be uncorrelated. Okay, that's why I said it's kind of part of this ICA somehow. So we apply PCA first and then we apply ICA. Because if we apply the ICA, then we have to update the parameters from scratch. But if we apply PCA, then we can get this uncorrelated solution with the closed form solution. It's just one kind of line. And with ICA, iteratively, we can get independent sources. Okay, that's it. Thank you.